And welcome back. As we continue our cosmic journey, previously we had looked at spectral lines, but now we're going to go ahead and take a look at something known as the Doppler effect, which can have a very real effect on said spectral lines. So when we previously left off with spectral lines, we kind of took a look at them, but now let's talk about decoding those spectral lines just a little bit. Astronomers can learn about the elements in stars and galaxies by decoding the information that's present in those spectral lines. Now, there is a complicating factor in learning how to decode the message that comes from starlight. If a star is moving either toward or away from us, its lines will be in a slightly different place in the spectrum from where they would be if the star was at rest. And if you think about most objects in the universe do have some kind of motion that's going to be relative to the sun. They're not going to be fixed with one another. And so, the first thing to understand is that motion is going to affect waves, and we're talking about light waves in this case. In 1842, Christian Doppler first measured the effect of motion waves by hiring musicians to play on an open railroad car as it was moving along the track. He then applied what he learned to all waves, including light, and pointed out if light is a source and it's either approaching or receding from the observer, the light waves will be respectively crowded either more closely together or they will be spread out. This principle of either cramming these waves close together or spreading them out is what we call the Doppler effect. So what exactly is the Doppler effect? What does that look like? Well, in this diagram here, we can kind of see the Doppler effect in play. In the first diagram, a source S makes waves whose number crests wash over a stationary observer. The light waves all spread out evenly. So here, the source is here, the observer is here. Neither one, you'll notice, is moving. And so because neither was moving, the sound is evenly distributed. Now, in the second one, the source S is now moving toward the observer. So you can see it's S1, S2, S3. So they're getting closer, and they're moving away from observer C. And you can see that wave crest 1 was emitted when the source is at position 1, crest 2, position 2, and so on and so forth. Now, the one thing that's going to happen, if this was light waves instead of sound waves, is that observer A is going to see these waves compressed by this motion. As you notice, the band here, these are getting more and more closely kind of tightly packed together, whereas in the backside, you notice they're getting further out. And what we do is we call this compressed motion here, we're seeing a blue shift. Observer C, because these are more stretched out, is going to see a red shift. Now, observer B, who is actually perpendicular to the source's motion, is actually not going to see any change. All right? So even though they're over here, they're not necessarily going to see any change because they are perpendicular to that source. So what does this Doppler effect really mean for the observers? Well, the Doppler effect is, of course, produced by a motion that, again, is either toward or away from the observer. And the motion that is happening here we refer to as radial velocity. Sideways motion does not produce some effect. It either has to move toward something or away from something. It can't move in perpendicular to it like we were just talking about. You can't be parallel either. Now, observers that would be, let's say, between point A and point B on that diagram would have some shortening of the light waves for that part of the motion source is along their line of sight. And also, if someone was on between B and C, they would also observe lengthening of the light waves that are along their line of sight. B doesn't, again, because B is perpendicular to that source. Now, you may have heard the Doppler effect with sound waves. This is something you're probably familiar with. So, whether it's a train whistle, police siren, ambulance, whatever it is, when they're approaching you and then they finally move away from you, you'll notice a decrease in the pitch of the sound waves. When they're coming up, they're very high pitched, and they kind of, the sound pitch changes as they're driving away. And compared to waves at rest, they have changed slightly more frequent when they're coming towards you to slightly less frequent when they're moving away from you. Now, with light, obviously we don't have sound, but we can have color shifts. When the source of waves moves toward you, the wavelength is going to decrease a bit. If that light is the source of our wave, then that manifests in the form of colors changing slightly. So as the wavelength of that light decreases, they're going to shift toward the blue end of the spectrum. Astronomers call this a blue shift. When the source is moving away from you and the wavelength gets longer, astronomers are going to call this a red shift. And remember, this has to do with the actual wavelengths themselves. That's why we call it a blue or red shift, respectively. Astronomers use these words to describe changes in the wavelengths of radio waves or X-rays, pretty much almost the same as we would describe the changes in visible light. So X-rays and radio waves can have the exact same behavior here as what you would expect to see with visible light. With visible light, obviously, yes, we can see it's going more blue or more red, but the same red shift and blue shift can also occur with the other wavelengths as well. And so that gets us into this whole thing with the Doppler after being a shift. So the greater motion, whether it is toward us or away from us, is going to cause a greater Doppler shift. So if we have just a small shift, it's going to be a small Doppler shift. If we have a large motion here, so let's say you're going back to the ambulance example, if the ambulance started up right next to you, you're not going to notice very much to it. But if the ambulance came from the other side of town and gradually approached you before driving away, you're going to have a much larger shift. Now, if the relative motion is entirely along the line of sight, the formula for a Doppler shift of light is going to be the change in lambda over lambda equals the velocity over c, where lambda is the wavelength emitted by a source. The change in lambda is the difference between lambda and the wavelength emitted by the observer. C is the speed of light, and v is the relative speed of the observer and the source in the line of sight. Now, in this case, the variable v is counted as positive if the velocity of one is of reception. So in others, it means that it is getting away from us. And it's negative if it is one of approach. In others, if it is getting closer to us. Now, that's all fine and dandy, but what does this have to do with star color? Obviously, we were saying, okay, there's a red shift, there's a blue shift, but if a star either is approaching or receding from us, one thing you'll notice that the wavelengths of light on the continuous spectrum either will appear shortened or lengthened, as do those of the dark lines that we see in that same spectrum. However, unless its speed is, let's say, tens of thousands of kilometers per second, the star itself does not necessarily noticeably appear to be bluer or redder than normal. The Doppler shift is thus not something that's easily detected in a continuous spectrum and can't really be measured accurately in such a spectrum. The wavelengths, though, of absorption lines can be measured accurately, and their Doppler shift is relatively simple to detect. So how do we know the elements, then, that are in the spectrum if we have to deal with Doppler shift? Well, if all the stars are moving and the motion changes the wavelength of each spectral line, again, you probably wonder, well, how do astronomers know what elements are present? After all, we know that it's the precise wavelength or color that kind of tells astronomers which lines belong to which element. And of course, we determined those elements by first measuring those wavelengths in containers of gas in our laboratories, which, of course, relative to us, weren't moving around. So if every star or every line that's in the star spectrum is now shifted by its motion to a different wavelength or color, how can we really be sure which lines and which elements we're looking at in a star whose speed we don't know? It's not like we got a radar gun out clocking a distant star and it's like, oh, that star is moving this fast. Well, the thing is, there are certain patterns in those spectrum lines that we can observe. Astronomers rarely judge the presence of an element in an astronomical object by one single line. That's just not going to be good data to look at. Instead, it's a pattern of lines unique to things such as hydrogen or calcium that enable us to determine, hey, those elements are part of the star or galaxy we're observing. Now, the Doppler effect does not change the patterns of lines from a given element. So even though it might red shift or blue shift, the thing is, it's still the same pattern. It is only shifting that pattern either more toward the red or more towards the blue. The actual pattern itself remains the same.